All right, let's get started now. Okay, so we got a lot to cover today. So make sure you're following along. Okay. So need a lot of energy being exerted today. Okay, as we finish up chapter 6. Okay. So let's first of all finish up substitution reactions. So in substitution reactions, remember we've looked at the substrate, okay? And there's one part of the substrate that we have not really looked at. What part do you think that is? It is the leaving group. The leaving group. So we want to ask what makes a good leaving group? Okay. What makes a good leaving group on the substrate? Okay. So in order to do that, let's look at a couple of reactions. Okay. Look at that one. If I were to give you that, you should be able to draw the substitution product. What would happen? The OH would substitute for the chlorine. Okay. So we get that alcohol as a substitution product. Or we could look at another substitution reaction. Let's say we looked at that one, where here we wanted what? The iodine to replace the OH. So get that substitution product. Okay, so hopefully that doesn't look too foreign to you. But now, let me give you some information. This top reaction turns out to be a favorable reaction, whereas this bottom reaction turns out to be unfavorable. Okay, you don't know why right now. I'm just telling you. And we're going to figure out why as time goes on. Okay? So you can see here that some substitution reactions are favorable, some are unfavorable. When we look at favorability, what are we looking at of a reaction? The kinetics? Not the kinetics, but the, what are we looking at? Favorability, what's it called? Favorability, not kinetics. Thermodynamics. Okay, so we're looking at the thermodynamics of the reaction to see if it's favorable or not. Okay. So that's what we want to figure out. How can we have predicted the top one was good, but the bottom one was bad, and so on? Okay. Well, the way we do that is going back to our acid-base theory. Okay. So remember when we looked at pKa values of acids. Okay. Remember, for example, HCl. Okay. The conjugate base of HCl is Cl minus. Okay. So here, remember the pKa of HCl was -7. Okay. How about if we looked at water? The conjugate base of water is OH minus. But what was the pKa of water? It was up around 15 or 16. Okay. So from our theory that we studied back in chapter 2, which of these two is the stronger base? Which is the stronger base? Still don't remember theory. Which is the stronger base? Cl minus or OH minus? That one comes from the weaker acid. Weaker base comes from the stronger acid. Better write it down if you forgot that. A lot of you forgot that. Write it down. Shame on you.
Okay, we'll repeat it.
And watch the video. Okay. So here,
Weaker base or stronger base?
No, weaker acid, weaker base.
stronger base.
Weak acid, strong base. Oh, I got it.
You need to be taking notes while I say things. So here we're going to see a very important rule that you don't want to forget. The rule is that strong base substitutes for weak base. Okay, very important rule. Very important rule. The stronger substitutes for the weaker. Never the weaker for the stronger. Okay. Is that what we have going on in the first reaction?
Yeah.
Does it follow in this rule?
Yes.
Yes. Stronger substituting for the weaker. Okay. So this is a favorable reaction. Okay. So anything that follows that rule is favorable. Okay. What about the bottom one? Well, the bottom one, we got iodide. HI has a pKa of about -9. So I minus would be what kind of base? A very, I heard it, weak base. So will the bottom reaction work?
Nope.
No. Bad. Trying to get a weak base to substitute for a strong base. That's not going to happen. So the reaction is unfavorable. Okay? Unfavorable. Okay? So here, strong. This one here is weak. Can't do it. It's got to be the other way around. Okay? So if I label these two reactions A and B, and I drew these two reaction coordinate diagrams, which one would match A?
The one on the left.
Okay, this one here. Because I got a downhill favorable reaction. This in here would be B, because I'm going uphill, unfavorable. Okay? So that's showing that the product is, yes, product is not very stable. Okay? So OH minus has instability with it, so it's higher energy. But over here, I have Cl minus. I like that. It's very stable. Okay. So a strong base is what? Unstable. A weak base is stable, and that's why I get the energy drop. Okay. Any questions on that? Very important principle. Very important principle that we'll use over and over. This is how you can predict whether it's worth doing the reaction in the lab. If you try to do this one, no problem. Someone asks you to do that, you say there's no use for me to waste my time. It's not going to work. Let's try something else. Okay. Any questions on this very important principle? Okay. You will see, I guarantee, more than one question on the exam about that. Okay, let's look at it from another angle. Okay. Let's look at it from this angle here. Okay. So there's our substrate. We already know that OH is what? A bad leaving group. Why? Because yes, it's a strong base. Well, now what we want to look at is a way to make that a good leaving group. And what we can do to make that a good leaving group is react it with H+. So the oxygen will get that hydrogen and so we get that there. Okay. Well, here, what has the leaving group turned into now? It's no longer OH. What is it now? It's water. Okay. So if I look at my pKa table, okay, water comes from H3O+. So to see if water is a strong or weak base, I need to look at the pKa of H3O+. And that turns out to be about 1.7. So 1.7 is pretty small, isn't it? So water is what, a weak base. So water will be classified then as a good leaving group. Because it's a weak base. Okay. And so this thing here will now be primed to do a substitution reaction. Okay. Just sit back there. It'll be something like an ether. An ether. Where this thing here is a bad leaving group. So, what do you think I can do to convert it to a good one? Add some H+. Okay. So if I add some H+, we get that. Very similar to water, isn't it?
Yes.
Except now the leaving group is what? An alcohol. Okay. So now, if I brought in a nucleophile, now the alcohol can leave. And alcohols are very stable, just like water, just like ammonia. Okay? So these are three ways, three different molecules that you can convert a bad leaving group to a good one. Okay? Just by adding some acid H+. Any questions on those? Okay. Okay. Any questions on this principle? Strong base substitutes for a weak base. Yeah.
This time will you give us the pKa values on the?
Oh, I'll give you the pKa's. I'll give them to you. All you gotta know how to do is use them. Is that a fair deal?
Yes,
How about you, is that fair?
that's fine. That's all I want. PK value.
Okay. You like pKa's?
I do. I love them. Wow.
I'll make sure to give you a lot of pKa's. All right, let's look at the last part of this part of chapter 6. Okay, this has to deal with Sn1 reactions. Okay, we've dealt with Sn2s. Now let's look at Sn1s. Okay. And let's start off by looking at this reaction here. see if we can understand Sn1 reactions with this. Okay, so here we have T-butyl chloride and water. Remember, you put solvent underneath the arrow if you have some. Okay, so remember how the Sn1 mechanism went. Okay, remember it was 2 steps. Okay, where the Sn2 was 1 step. Okay, that's the first point of difference. Remember what happened in the first step of the Sn1? The leaving group leaves. Okay. So if the leaving group leaves, then you form these ions. Okay? This is always what happens in the first step. In here you have a carbon with a positive charge. Carbon with a positive charge is called a carbocation. Not a carbocation, but a carbocation. Then in the second step, the nucleophile comes, and where do you think that attacks? Positive charge. So it adds on there. So the water has added on. Again, note, water is 3 bonds, so it has a positive charge on the oxygen. And when I have that, that makes either hydrogen acidic. Okay? Because that oxygen is squeezing in those electrons. It wants to get rid of that positive charge.
You said one of them is acidic?
Either one. So, since either are acidic, I could bring in a base, such as another water molecule, and get my final product. Okay, which here would be T-butyl alcohol. Okay, so this is how the Sn1 mechanism works. Okay, now based on this reaction, we're going to understand the parts, okay, and the theory of Sn1. Let's go to the first part of understanding. Okay. Note that a carbocation form. Okay. There turns out to be different types of carbocations. So let's address those.
Excuse me, Dr. Wilkin.
Question?
Along with this alcohol, there's a H3O plus polyatomic ion with that. Because the water, it took that other hydrogenation.
Yeah, that's just a side product. So we can write that on the side. I'm just concerned about the main product. A good
I
question.
want to make sure I understand.
Oh, yeah, good question.
Is that not,
Be thorough. Yeah.
does that not combine with chlorine to make hydrochloric acid
Or chlorine.
from the carbon cation?
Yeah, so either the water could come, or Cl minus could take that and give you HCl. Okay, so you probably have a mixture here. Okay, good observation. Okay, so the Cl minus we got here, so that could come and form HCl.
We are.
All right, let's look at types of carbocations. Let me draw some different types. Okay, these follow the same series as radicals. Okay, so here, this will be what? A primary carbocation, secondary carbocation, and tertiary. Okay? And the stability order follows the same as radicals. So what would be the most stable? Tertiary. Okay. And the primary would be the least stable. Okay. The reasoning for that is that, remember, carbons are electron donors, so the more carbons I have, the more they can donate to help offset that positive charge. The fewer I have, the fewer I have to offset the positive charge. Okay? So that's why the tertiary is most stable. Well, that makes sense down below why I chose this molecule, isn't it? Because I get a tertiary carbocation. So Sn1 reactions work best for what? Tertiary alkyl halides. Okay. So Sn1s, another characteristic, tertiary is the best. What was the best for Sn2s? Primary, CH3s. Okay? So another difference, Sn2's primary is best. You may want to develop a chart to compare Sn1 and Sn2. So far we know two differences.
Can you put that in a complete sentence? Sn1 reaction, tertiary is best.
And Sn2 primary is best.
So when you have a tertiary, I
A
guess
tertiary
molecule, then you-
substrate.
There you go, substrate, then you definitely want to use this one.
Okay.
And
So-
Sn2 for the primary.
Okay, so fine.
So if I have a tertiary, when the leaving group leaves, I get a tertiary carbocation, so that would be the best stability. If I tried a primary or secondary, I would get a less stable carbocation, so that wouldn't work as good. See that? So that gives a more downhill reaction. I get a more stable carbocation. Does that help?
Yes.
Okay, so that's a second point of difference. Okay. Let's look at a third point of difference. Look at the nucleophile. Is that a strong base or a weak base?
Really?
Pretty weak. Okay, so here is the tip-off to know if the reaction is an Sn1. Okay, Sn1 two things to look for: a tertiary substrate and a weak base as the nucleophile. That was the total opposite of SN2, wasn't it? SN2, I wanted primary and a strong base. Okay? Let's look at the next point of difference. Keep track. Keep with me. Okay? I know we're covering a lot here. This has to deal with the solvent. Okay? We saw the solvent factor in SN2 being what? Polar aprotic, right? So I don't form the solvent gauge. Well, here, what this solvent is doing is saying as long as I'm polar, I don't care if I'm protic or aprotic. What I'm going to do is I'm helping to remove the leaving group, or to put it in a better way, I am helping to ionize the substrate into ions. Okay, that's the purpose of the solvent here. I just want to ionize the substrate. Okay. Into these ions, and we say the ability for a solvent to do that, we give it a special name. So it's what's called the dielectric constant. The dielectric constant is the ability, is the power of the solvent to ionize. And it has this symbol here, epsilon. Okay? To give you some examples of a dielectric constant, water has the highest dielectric constant of around 84. That's why it's sometimes called the universal solvent. Okay? So it's able to easily ionize things. Okay? One with a very low dielectric constant might be something like hexane, which maybe is around 1. Okay? So if I try to do that reaction in hexane, it wouldn't ionize it, and it would just be a dead reaction. Okay? So generally, polar molecules tend to have high dielectric constants. So as long as the solvent is polar, I'll be in pretty good shape. Okay. Any questions on the solvent effect? Okay, so those are some major differences. There's one last difference. Let's tackle that. Okay, and this last difference deals with the stereochemistry of the reaction. Okay? For an SN2 reaction, let's look at that first. Suppose we were doing the following SN2 reaction. wanted to do a substitution on 2-chlorobutane, note it has a chiral carbon there. And let's suppose that chiral carbon was R, the R enantiomer only, okay? So it's 100% R. And after I did the reaction, note I still have the chiral carbon. But what I would find is that it would invert to the full S enantiomer. Okay. So here for Sn2 chemistry, we get 100% inversion. 100% inversion of the chiral center. So if I have R, it'll go to S. If I had started with S, it would have converted to R. Okay? And we give that a special name. We say that the reaction is stereospecific. Okay. So Sn2 reactions are stereospecific reactions.
All the reactions gonna be like
All Sn2s. Okay. Well, how does it differ from Sn1s? Okay. For the Sn1, let's just say we had a molecule where we're looking at the R enantiomer only. We won't draw one. Let's just say we had one. And then we did the reaction. What you would find is you would get a mixture of R and S. You would end up getting a mixture, okay? And with the inverted one, you would get a little bit more than the non-inverted one. So you don't get a racemic mixture, which was what, a 50-50, but you just got a little bit more, maybe 60-40 or 70-30, something like that. And here, when this happens, we say that the reaction is stereoselective. So Sn1 reactions are stereoselective. Sn2 reactions are stereospecific. Okay? To use the same diagram for Sn2, that's how comparison would be. You only get the S. But for Sn1, you get the mixture. Okay. Any questions on the stereochemistry?
That's vice versa as well, right? Like if you use S only.
That's right, that's right. So if I would have started with S only, I would have got only the R. S here, I would have got more of the R that time. Yeah.
And then for Sn1, when we do R only, the racemic is gonna be more of the S?
No, you don't get a racemic
I
mixture.
mean,
You get a mixture,
the 60/40.
you get a mixture where you get more of the S.
Okay, so if we start out with the S, then we're gonna get more of the R?
That's right.
That's fine.
Okay,
Thank you.
good. Get that cleared up.
The reason it does that is because SN1 has more steps to it, or
We didn't get into it, but what happens is that the leaving group shields the same side attack, and so you get more of the back side attack to start with. And then as the leaving group leaves, then a front side attack can start happening.
Is that what we talked about when you said the nucleophile attacking the back?
That was for the SN2.
Okay, yeah, it was.
So for the SN2, it can only attack the back, so you get the inverted.
Okay, yeah.
Okay, so you can read the textbook, it gives you diagrams to see how that's happening. Anything else? Okay, so that website is now working. I know there was some trickiness going on, but it's flawless now, it's as smooth as silk. So you can get in there, practice those problems. This is the end of the material for our exam next Wednesday. It's going to be nice and cold this weekend, so hopefully that'll keep you studying. Okay, get in those exercises to get your brain warmed up, practice stereochemistry, practice chapter 4 stuff, and then get into this substitution stuff. We'll see you Monday.